What is the difference between a discrete random variable and a continuous random variable? Let's look at men's shoe sizes. Shoe sizes are discrete random variables. They take on individual countable values. You can't have something in between a size 7 and a size 7.5. Nobody's heard of a size 7 1/8 shoe. On the other hand, the length of a person's foot is a continuous random variable. This shows approximately how long of a foot fits in each shoe size. But unlike the shoe sizes, we could have someone who has a foot length that's in between 24.6 and 25 centimeters. And in fact, there's an infinite number of possible values between 24.6 and 25. For example, 24.6002 is between 24.6 and 25. So that's the difference between a continuous random variable and a discrete random variable. Now let's look how mathematically they behave and how we handle them when we're dealing with probabilities. If we have a discrete random variable, like we had, we can make a little chart. So let's say this would represent sizes 6 and 6.5, 7 and 7.5, and so forth. I didn't put the halves in just to make this a little smaller. And let's say that these are the probabilities of randomly selecting a man, and that would be his shoe size. Okay, so we have all these probabilities, they add up to 1. So this is a discrete random variable. It has a finite countable number of outcomes. Now the probability that x is equal to 10 is 0.2. The probability of that x is greater than 10 would be 11 or 12, 0.15 plus 0.1, 0.25. The probability that x is greater than or equal to 10 then would be the sum of these three probabilities and be 0.45. These were some things that we did earlier. Now how is that different from a continuous random variable? In a continuous random variable, you have the infinite number of possible outcomes. So if this represented men's foot lengths here and in inches, up there I did centimeters, but here inches, it looks like about 9 to 12 would be realistic for shoe sizes or foot lengths. So I used 8 to 12. So these are just kind of my ideas. So let's say 8 to 12 inches, and I wanted to find probabilities. Could I make a chart and list all the possible foot lengths and their probabilities? No, that would be impossible because there's an infinite number of possible foot lengths. So the only way to find probabilities for foot lengths is to make what's called a density curve. In this case, it would be easy to imagine that the majority of foot lengths would be around some average number of inches. And I think I read that 10 to 10.5 inches was the average foot length for a man on the internet. So that's why I picked 10. We would have a smaller number of very large feet and a smaller number of very small feet. And it turns out that a normal model is a pretty good approximation for the distribution of foot lengths. You could imagine if we had lots and lots of individual foot lengths and each one of them we had a little bar showing what the probability was, and I put lots and lots of little tiny bars, that if I made the bars small enough, eventually it would turn into a curve that looked pretty much like this. So to find the probabilities for various foot lengths, I have to use the area under the curve, and we learned how to do that with a normal model. But look at the difference here. Of the three probabilities here, I can only find one of these three. I can't find the probability that x equals 11 inches because that would be just this line right here. And this line doesn't have any area because there is no width to the line. So since the area is 0, it's not possible to find the probability that x equals a particular value like 11 inches or 11.001 inches or anything like that. I can find the probability that x is greater than 11 inches or x is greater than or equal to 11 inches, and those turn out to be exactly the same because both of them turn out to be the shaded area here. Whether or not I include or don't include the boundary line doesn't make any difference in the area that I calculate. So there's only one thing I can do is calculate area. Now this is done using calculus, which is not part of this course. If you did take calculus to find the area under the curve, you would use an integral. And so it is possible to use the equation of a normal curve and find the integral from 10 to infinity or 11 to infinity and find the area under the curve. That is what your calculator is doing internally when you do normal CDF, the normal cumulative density function. Recall that to find the area under a curve, you use the left bound, which in this case would be 11, the right bound, which in this case would be positive infinity, and then put in mu and sigma, 10 and whatever sigma would be here, and that would be calculate the probability or the area under the curve.